Anybody have any questions for me? So I always ask for questions now because, well, inevitably in a class this size, I get asked the same question dozens of times. So it's better that you ask it now in front of everyone because there's probably 10 other people in the room who have the same question, and then they won't have to come see me. So how's it going with the assignment? Okay, how many of you are done and have 100%? Okay, good-ish, yeah. Good. If you're not done and have 100% yet, then you know, get to work on it. Get started. I hope not too many of you haven't done that yet. The deadline is approaching. Yep.
When is the server not going to be beta?
It should have been last night, but apparently it's still beta right now. Soon. The TA is ready. He asked me yesterday if he should make it live, and I said yes, so I'm waiting for him to flip a switch somewhere. Yep.
What day is the midterm?
October 21st. Friday, October 21st, the day before the reading week. Yeah. So you won't have to read during reading week, at least not for this course. Okay. So how's the volume level? Yeah? Okay, good. So today I want to talk about a different aspect of efficiency than what we've been looking at, and that's memory efficiency. And even for people who worry about memory efficiency, we'll be looking at a finer level of detail than is normally looked at. So all of the implementations of lists that we've seen so far are, from a rough point of view, they're memory efficient in the following sense. A list that stores n items uses O of n memory. Okay, if we think about this for a little while, we'll realize that that's true of all the list implementations that we have studied. They've all been array-based, and they all use one or two arrays that are at most 3 times bigger than the number of items in the list. So if there's n items in the list, they might be using an array of size 3 times n, but not bigger than that. And that's true even when we looked at something like the dual array deck, which glues together 2 array stacks. Well, each of those is only 3 times bigger than necessary to store the items it contains. So in total, the sum of the 2 sizes of those 2 arrays is not more than 3 times the number of elements in the dual array stack. So they're all efficient in that sense. Now, remember, for those of you who've looked carefully at the definition of this big O notation, this hides constants. So 3 times n is the same thing as n when you're talking about big O notation. On the other hand, when you're buying a computer, for example, and you're talking about how much memory or RAM is available in that computer, you don't usually say, oh, well, you know, 4 times n is the same thing as n, so 4 gigabytes or 16 gigabytes, who cares? It's all O of n, or 1 gigabyte, it's all the same thing, right? So this, I mean, while it's a useful tool, because it abstracts neatly away from constants, sometimes this big O notation is hiding a little too much. And indeed, you know, if you're shopping for a computer, you it's a big difference to you whether the thing has 16 gigabytes of RAM or 4 gigabytes of RAM, or 1 gigabyte of RAM, all of which big O notation doesn't care about. In fact, big O notation would say that it has O of 1 RAM in that case. So it has a constant amount of memory, it doesn't change. So we want to look at a little more detail at this idea of memory use. And I gave you a definition last class. We'll talk about wasted space. Okay? And that is any space, memory, that is not used to store a, let's say, unique occurrence of some item in the list. Okay? So that's the thing we're looking at. Now, we need a unit of measurement, and we'll say that that is measured in words. And what's a word? Let's say 1 word is big enough for 1 list item, or 1 pointer. Okay. So words, let's say on modern computers, they're either usually 32 bits or 64 bits, depending on whether you have a 32-bit or 64-bit processor, or rather which mode that processor is running in. So that's the thing we're counting, is the number of wasted words. And so we see that, in things like a list that's implemented as an array, like the way Java's array list works, or the way our ArrayStack or ArrayDeck works, there's a lot of wasted space. So some of this stuff is used to hold list items, the indices 0 through n, minus 1, and the rest of that is wasted space. And that's not the only wasted space. There's also a little bit more. There's this integer n that we're storing to keep track of the number of items in here. And there's also this pointer a, which we don't hardly ever even think about. But because we have an array like this, we need to store a pointer to it. And that pointer is not a list item, so it's a piece of wasted space. Okay. So, in this implementation, the wasted space is O of n, and it's also omega n. So it's at most a constant times n, and in many cases, like right after you resize this thing, it is also 2 times n, or 1 times n. Okay. So there's a lot of wasted space here. And you might think, oh, okay, well, maybe I could use, maybe the problem is with this way we're resizing these arrays, that we're storing things in arrays, and to make growing and shrinking be efficient, we end up with these cases where there's a bunch of empty space in the array, so we don't have to resize too often. And linked lists don't have that problem. Linked lists only allocate exactly the number of nodes that they need to store their elements. So a linked list would look something like this. This one's null. So So you might have x1, x2, x3, x4, up to xn. So is this any more space efficient? Does this waste any less space? Yep. Yep. In a linked list, yeah, you have exactly the number of list nodes that you need, but each node has two parts, at least. One of them holds a list item. That's good. That's not wasted space. But the other thing it holds is a pointer to the next item in the list. Well, that's not a list item, so that's wasted space. And there's n of those things, and so the wasted space is also proportional to n in a linked list. So they're not space efficient either. Okay? So we want to know, can we do better than this wasting a linear amount of space? And can we do this, let's say, in an efficient way without costing too much? So the first thing you might think of, if you don't care about efficiency, is say, well, these array-based things, they're not bad, right? The array is half full. And we could change that slightly to make the array more full. So in fact, we saw the first thing we tried when we talked about growing and shrinking arrays is that when we need to grow an array, because we're about to add something to a full one, we just make it give it one extra array location. Now it turns out that that was inefficient. It took too long to do that. It was very slow then when you added a bunch of things because you're allocating a new array each time. But is that space efficient at least? Yes or no? So the answer is, it is sometimes, but there's a point in time when it's not efficient at all. And if you think about why you want space efficiency, it's because you have a limit in the amount of memory that you have available, and you're trying to avoid running up against that limit. Now, suppose this thing is full. So that means it has n items in it, and that's the length of the list. And now I try and add to it. So what happens? So resize is called. What does resize do? It copies the array. Copies it into what? A bigger array. And those things had names. This one was called A, and this one was called B, and we're about to swap them. But before we do that copying, and even while we're doing that copying, how much wasted space do we have here? N. This whole array is wasted. It doesn't contain list items. And so you might say, oh, but that's only for temporarily. But actually it's not. It's as long as it takes us to copy all of this data over. So it's not a short amount of time, actually. And so this also has wasted space proportional to n. During the time when we're copying this, these are not unique. Each element appears twice now, so one of those is considered wasted space. And right up until the point where we free this array, go to allocate B, and your system says, I can't allocate this memory because I don't have it available. So this is not any better. Just changing the schedule by which we grow this thing to not double each time doesn't really save that much space. Okay. So today we're going to do something kind of cool. And that thing is we're going to make use of something you learned, well, I hope you learned at some point before you arrived at university, quadratic equation. Anybody remember that? Does it ring a bell? Have you heard the phrase before? Yeah, okay, good. I haven't been following developments in teaching of mathematics in high schools lately, so it's possible that that some of you got here without ever seeing that. So we'll get to that soon. What we're shooting for is to really cut down on the wasted space. I want to go from something that's proportional to n to something that only wastes at most the square, something times the square root of n. Okay? So if n is 1,000,000, then I'm willing to waste something like 1,000 memory locations. In fact, it'll be a few thousand, but it's not going to be a few million, unlike what happens with the usual structures. Okay. So here's the idea. We're going to take our list, and we're going to store its items in arrays. That'll be nice because that'll still give us this constant time get and set operations, which linked lists don't have. But it's not all going to be one big array. Because whenever we put everything in one big array, we'll always run into this problem that we have to allocate a new one, and right there we're going to have difficulty. So we're going to put it in, spread it out a few different arrays, and we'll start by using a single array that can hold a single item. So let's conceptually build this thing. So we want to have a single array that holds a single item, and so we do that. That's no problem. Somehow we'll need to maintain a reference to that. Well, in the case when n is 1, then we're already wasting a pointer for one item, but we're not going to have much choice there. And now when we want to add something, well, it doesn't fit there, so we'll allocate a new array. How big should the new array be? Yep. Double the size. That's true, and that's what we'll do in this case. We'll allocate a new array that's twice as big. And we'll take that new thing we want to add, and we'll put it there as the first element of this new array. Let's say we want to add it at the end, if we're appending at the end. So we can think of this now as, here is list item 0. Here's list item 1. Now if we want to add something, we have space. So if we want to add a z, well, before that, we now need another pointer to point to this thing. We can't lose that array, so we better hold on to it. And you can sort of see that, well, if we continue this way, we're going to end up with more than a constant number of pointers here. These number of pointers are going to increase. So we're going to need some data structure that can hold those pointers. Okay? And now if we want to append another item to this list, we're okay. We have room for that. We can add a z to the end of this list, which puts it at list index 2. So if you ask me to get the 0th item in this list, I'll tell you it's x. The first item, the 1th item is y, and the 2th item is z. And now what happens if I try and add one more thing? What's that? Okay, so the suggestion is that it doubles again. So that would have us creating a new array. And putting our new item here. So a new array of size 4 and putting our new item here. So let's think ahead a few steps and see if that's going to get us what we want. Remember, we're shooting for wasted space proportional to the square root of n. So imagine we've been doing this for a while. So we've been doing this for a while, and so we have actually k of these arrays here. So each time we've been doubling, and so that means that this last array has size 2 to the k minus 1, right? This has size 2 to the 0, this has size 2 to the 1, this has size 2 to the 2. So that means that the k minus 1th one must have size 2 to the k minus 1. Okay. And when that was allocated, it was because all of these other ones were full leading up to this. And right at the time it was allocated, it was completely empty. So it was wasting space at that time. So how much space was it wasting? Well, how many items can all of these hold if each one is twice as big as the previous one? So if all of these are full, wouldn't it be what?
The next one is like n times 2.
So if we call the sum of all these things n, so that means n equals 1 plus 2 plus 4 plus 8 plus 2 to the k minus 2, if this one has size 2 to the k minus 1. Anybody know what that adds up to? So here's a hint. I can take all of those things and pack them into here. If I take this one, the last one, it'll fill this halfway up. And the next one will fill this thing, the remainder halfway up, and the next one will fill the remainder halfway up, and so on. So this is actually 2 to the k minus 1, and I'll still have space for one more at the end of this thing. So that's not good news for us. So that means before we added this last item, n was equal to 2 to the k minus 1 minus 1. And then we allocate a whole new array whose size is n plus 1. And that's wasted space at that point. So again, we'd be wasting a linear amount of space. So we did something wrong here. And the thing that we did wrong was to assume that since doubling had worked so well for other problems, we should continue this idea of doubling. And that's where we went wrong. So we don't double like that. So forget all of that. Go back to this step when we were deciding how big this third array should be. So doubling doesn't work. What should we try next? Yep. 3. Let's just make it 1 bigger than the previous one. Okay. And then we put our new element there. In terms of list indices, this is list position 3, 4, 5. And we're good to go for another 2 insertions. If this goes to another step, if we need another list, or another array rather, then this would be 6, 7, 8, 9, and so on. So this is going to be what we use for our, this is going to be our representation of a list. Basically, we have a sequence of arrays of size 1, 2, 3, 4, 5. The 0th one, I mean, we pack them, we pack our list items into those arrays in that order. So the index in the list somehow is related to which of these arrays you're in. Yeah, and so that's it. We need to keep track of all these arrays that we've been allocating, so we'll use something here. And, well, I think it's not too hard to see that as this thing grows, as our list that we're representing grows, we need to add new things to the end of this. And maybe when it shrinks, we might have to remove things from the end of this. So for example, this structure here is also an array that can grow and shrink. And for that, we'll use an array stack. Or if you like, in the Java collections framework, that's an array list. Okay. So we'll have to worry about that. This involves some wasted space. We have to account for that when we're counting up how much space we're wasting. And we'll go on like that. Okay. So, first question. Let's say we're trying to figure out how wasteful this thing is. How much space are we wasting? So, you know, we've added some stuff to this. Been doing that for a while. So we are at the k minus 1 index here, which means this is a list of length. The next list that we're going to allocate has length k. And right at the time we allocate it, it's completely empty, so it's wasting space. So we need to figure out what is this value of k compared to the value of n. Okay? Because that's wasted space, and we want to compare that to the value of n. So the question is, in this picture, if all of these are full, then n equals what? Well, it equals 1 plus 2 plus 3 plus all the way up to the last one, which we did this before. Yep. Yep, divided by 2. Yep. This is equal to k times k minus 1 divided by 2. A nicer way to say that is that this is k squared minus k, and I'll even separate those things out. So the important thing here is the k squared. So n is roughly k squared, okay, in terms of these asymptotic notation. N is theta k squared. It's at least a constant times k squared, and it's at most a constant times k squared when n gets big enough. And here we're wasting some space. And so let's see where the wasted space is. This last array is completely or partially empty. So if we count our wasted space, we have k wasted space in the last array. Where else do we have wasted space? In this array stack, that's all wasted space. How big is it? It has k items in it. It's a growable list, so it might be twice as big as necessary. So maybe it's 2 times k or 3 times k. So we have at least a constant times k wasted space for the array stack. Probably we should also do a bit of bookkeeping here. We will keep track of the value of n. Usually that's kind of helpful. So we'll have a constant wasted space for n and any other kinds of little bookkeeping things we want to do. Okay. So here we've been writing it in terms of k. If we rewrite that in terms of, so in total this is k plus 1. This is, in total, it's only O of k wasted space. But if we write that in terms of n, well, n is k squared. So that means k is the square root of n. Okay? Any questions right now? If you made a bunch of these, well, that's not going to help us because we still would have to keep track of k things. Okay, so we run into a problem there. You can try some other balancing tricks, and what you find is either, you can try different schedules, and what you'll learn and what you'll see is absolutely necessary, is that either you end up with a big array that wastes a whole bunch of space, or you end up wasting a bunch of space keeping track of the arrays that you have. Right? If you keep all your arrays small, then you need a lot of pointers to keep track of them. If you make one too big, then when you allocated it, it was wasted space. And we'll see actually you can formalize that and show that you can't do better than this. That the trade-off happens when these two quantities are about the same, right? Here, the biggest array is of size square root n, and we use square root n space to keep track of all the arrays. Okay. Now, that's great. This seems to do what we want it to do, but now we have to make all this work. We have to be able to add, remove, get, set, and all of those things in this data structure. Yep.
What is that theta stand for?
Theta, in this case, we can say this is the same thing as saying n is O of k squared, and k squared is O of n. So big O notation, people usually forget, it only provides an upper bound on the thing on the left-hand side. So this just says n is less than or equal to some, well, not this. This says n is less than or equal to some constant times k squared. But it's not just less than or equal to, it's actually also bigger than or equal to some other constant times k squared. Yeah?
Should the last array have k
Well, these arrays are indexed 0 through k minus 1, but the 0th one has 1 element, and the 1th one has 2 elements. So their sizes are 1 through k. Their indices are 0 through k minus 1.
Yes, so the last one should have k elements.
Yeah,
So why is it k minus 1?
because this 1 plus 2 plus 3 plus, oh, you're right, okay. Yeah, you're right. Good. Thanks for catching that. So that is k times k plus 1 over 2. Okay. Good. All right. Okay. Now we have to make everything work. So the first thing we want to do is the get operation. The whole point of a list is to store items so that I can access them by index. So if I say, you know, get 2 on this list, I expect you to return Z. If I say get 8, I expect you to return this squiggly thing here. So we have to figure out how to implement that. And we want this to be as good as something like an array list, and that means we should be able to do it in constant time. Any idea how we do that? No. So one thing you could do is make an array of size n, and for each one keep track of where the thing is you should store it, but then that array would be wasted space. So we need something other than that. Yep.
So we need to know what index to look at in the array stack pointers, which means we can find out what gives the length.
Yeah. So two things we need to do. First is we need to know which of these arrays the element we're looking for is in. And that means which index we should be looking for in here. And then once we get there, we need to know where the index is in that array. And we'd like to do all that in constant time. So let's figure it out. Okay. So I'm looking for index, the thing that's holding index I. And so there's two things I want to figure out. B, that should be the index of the subarray that contains index I. And then I'm also interested in J, and let's call that subarray, I don't know, A. The index in A of the element at list index I. Okay, so for example, if I take I is equal to 5, then I want B is equal to 2, because I want this subarray, and I want J, 0, 1, 2, to be equal to 2. So go to this subarray and take the element at index 2. That's the element I'm supposed to return for 5. Okay, so that's an example. Let's start first guessing that we know, pretending we know B, and see if we can figure out this index J. Okay, so we know B. So this is B. And someone is telling me that the element at list index I is somewhere in this subarray. What I need to know is where. So if you look at this, well, this subarray, for example, starts with indices I equals 3, 4, and 5. And that's because there's 3 things in all of the that came before it in these arrays. This one starts at 6 because there's 6 things here. So really all we need to know is how many elements are there in all of the arrays before B. And that's where we can start counting from. Okay. So in all of these guys, there's 1, 2, 3, and so on. So the number of things in there is 1 plus 2 plus 3. That's the one that goes up to B minus 1. And that's B times B minus 1 over 2. Okay. So the index of the first guy in the Bth block is B times B minus 1 over 2. So if I is equal to B times B minus 1 over 2, this should be the value of J, 0. And in general, the value of J should be equal to I minus B times B minus 1 over 2. We can check that. 3, 6. Three times 2. Box. There's an integer n that keeps track of things. Here's the method for computing the index. Given an index I, turn it into a block index B. And indeed, it just evaluates this equation as a double and then converts that into an integer. And I've checked this. This works correctly for all roughly 2 billion possible indices that you can have as an integer. So it works correctly for I equals 0 up to 2 to the 32 minus 1. Sorry, 2 to the 31 minus 1. So that rounding is not an issue here. And there's the code for get. So check to see if you're trying to index out of bounds, get the block index, get the index within the block, and then return that item. And set works exactly the same way. So nothing too surprising there. Okay. How about if we want to add to one of these things? So if I want to add a new value to one of these, how would that work? Yep. Pardon me? Yeah. So, if we want to put something into one of these, like for instance, if I want to say something like maybe add 4x, so that means I want to add it here, but there's already something at position 4 and position 5, 6, and 7. We need to do shifting. Now at first this looks complicated because, you know, that means the thing at position 4 needs to get shifted off to here. This one would fall off the end, so it needs to come back here. This one would fall off the end, so it needs to come back there, and so on. But it's not actually complicated because we've already solved the two problems that we need to solve in order to make this look easy to us. We have get and set methods for the indices that take indices and translate them into blocks. So actually, it's just the usual shift, except instead of using array bracket notation, we just use get and set. Okay? This is not exactly the most efficient way to do it because we're constantly solving quadratic equations for every index. You could optimize this, but if you just want something that works and is easy to understand, then that's clear. But this also shows something else we need to do. And it's the same issue we always have when we implement a list using an array is sometimes, or using many arrays, sometimes we're full and we need to grow. Okay, so R is the number of blocks. This then R times R plus 1 over 2 is the number of elements we can store in all of those blocks. And if that's smaller than n minus 1, that means this thing is completely full and we need to grow it. So that's what we do. And the grow code just looks like this. To our list of blocks, we add a new array whose size is equal to the size of the list plus 1. Okay, we just add another block at the end that's one bigger than the biggest block in there. All right. Does that seem okay? If we need to, we add a new block at the end. Then we do any shifting that we need to do. And then finally, we write the value where we want to write it. Yep.
All this, like, every time you do the equation, it's still constant.
Well, where are you doing these equations? I mean, where are you solving quadratic equations? Yes, each one takes constant time. And where you're solving them, in this case, is in these get and set methods. But remember, the number of get and set methods is just equal to the number of items that you're shifting here. Okay? So this basically, you know, within a constant, this has the same kind of running time as an array stack. This is basically the running time to add. So, you know, if, and this is really sloppy, if arrays are full, you grow. And notice that growing is actually quite a bit simpler than in an array stack. You don't copy anything. You just create a new array at the end. And now the next thing you do is shift elements I up to n minus I to the right. And then you finally set I to be equal to x. That's all add does. And this is just done a little bit differently than an array stack, but I mean, it's still, the time that it takes is proportional to the number of elements that you're shifting, and that's n minus I. N minus I. The number of elements that you're shifting is n minus I. This here is, right. It's elements at indices I up to n minus I. n minus 1 rather, that's n minus I elements there. Okay. So no real surprises there. How about remove? What's that going to look like? If I want to remove the value at index I. Yeah. 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 So you do something like shift elements at positions I plus 1 up to n minus 1 to the left. If you want, you can set the element at position n to null and n minus minus. Here, I guess we should do the n plus plus. Set that to null, and that's it. Your value is removed. Anything else we should do? We should maybe shrink. And when should we shrink? Oh no, 2/3 would be way too much wasted space. Yeah. Okay, so if the last array is empty, and that we can actually figure out by doing some calculation like, the last array is empty if r times r minus 1 over 2 is bigger than or equal to n. That would mean the last array is empty, something like that. So we can test this condition. And then we do something like shrink, which removes the last array. Okay. Is that a good idea? So there's one little issue here. So this runs into a problem that we call thrashing. Comes up in a lot of contexts. So let's say this is all full. And now I add something. So I add a new array. That takes a while. That takes about, this is k or whatever you want to call it. This is about square root n. And I add the new thing here. And now I remove something. In fact, I remove this thing that I just added. Well, according to this then, this last array is empty, so I should delete it. So I do that. I go through all the effort of deleting this thing. And now the next operation is going to be what? I add something again. Now I have to allocate this whole new array again. It gets all initialized, everything gets set to null, and I put this thing back in here. So I am only adding at the end and removing from the end. That should take constant time, but suddenly everything is taking square root n time because I keep allocating and deallocating this array. What's the solution? Yeah. The only thing you need to change here is to change this to say, not if the last array is empty, but if the last two arrays are empty. Then you remove one of them. And that actually makes all the difference, because now if I add and create this new array here, and then I immediately remove, there's only one empty array. So I'll leave it there. In fact, I have to remove a lot before I will even get rid of this array. And the number of elements that I'd have to remove is actually equal to the number of elements in this array. I have to remove the one here plus the k minus 1 elements in the previous array. And we've seen now a few amortization arguments that work this way that basically say, you know, whenever I have to deallocate an array of size k, so whenever I have to delete an array of size k, that's because I have done at least k deletion operations that led up to that state. Okay. So that growing and shrinking, as long as you allow up to 2 arrays, empty arrays at the end, doesn't add anything to the amortized cost. So it's just a constant per operation. And so indeed, this is what the remove method does. If you check this formula, this is really checking to see if if we could have fit everything even after removing, decreasing the value of r by 2. Okay, so decreasing the number of blocks by 2. And what does shrink do? Shrink removes things, just does basically that. Removes things until we have at most 2 empty blocks. Okay. All right. So this array, this thing, it's called a RootishArrayStack. Right. B I got that wrong. If this is at index B, it contains B plus 1 items, meaning these ones count all the way up to B, meaning that there are B times B plus 1 of them divided by 2. And that's where I should start then. B times B plus 1 divided by 2. Let's check that in this picture. At index 3, 3 times 4 is 12, divided by 2 is 6. That's the starting index here. At index 2, 2 times 3 is 6, divided by 2 is 3, and that's the first index here. Okay, good. So this is the value of j we're looking for if we know the value of b. All right. Now how do we get the value of b? So if we think about, you know, our original implementations of a list, where we imagine these things being stored in an array, at position I here, we count how many elements there are leading up to and including this thing. Well, there's I plus 1 elements here, right? From here to here. This is I plus 1 elements. Okay? So if you ask me, for example, for the element at index, let's say, 7 in this list. Okay? So I know by looking at this picture that this is the one that I'm looking for. So at index 7, there's 8 elements up to and including that index. The things at indices 0, 1, 2, 3. all the way up to 7. So imagine, searching for this programmatically, and you'd say, well, am I looking, is the thing at index 7 in this list? And the answer is no, because there's only one element so far in this list that's less than the 8 elements that I need. Is it in this list? No, because there's only 3 elements so far. That's less than the 8 I need. Is it in this list? No, because there's only 6 elements so far, and that's less than the 8 I need. Is it in this list? Yes, because there are 10 elements so far, and that includes the 8 that I need. So if you think about that, what that's really doing is, what we're doing is counting how many elements there are in these lists until we find the first value where that exceeds I plus 1. And so in the first b plus 1 lists, so the first b plus 1 lists contain b plus 1 times b plus 2 over 2 elements. And we want the smallest b such that b plus 1 times b plus 2 over 2 is bigger than or equal to I plus 1. So that's what we're looking for. The smallest value of b that satisfies this equation here. The smallest integer b that satisfies this equation. So what kind of equation is this? Yep. It's a quadratic equation in the variable b, right? So this is something like, well, we can rewrite this as b squared plus 3b and minus 2i is bigger than or equal to 0. Now, is that a quadratic equation in B? It's a trick question. Quadratic equation, what word is somehow implicit in equation? Equals. So it's not a quadratic equation, it's a quadratic inequality, maybe. But lucky for us, we can fudge this and say, well, let's make it equal. We can solve that and get a value of b where this thing is equal. What's the problem with that value of b? Well, there's 2 possibilities, but actually if we solve this, we'll see that there's only one useful one. And so you solve this and you get b is equal to minus 3 plus or minus the square root of 9 plus 8i over 2. So there's 2 solutions, minus 3 minus this thing and minus 3 plus this thing. Well, minus 3 minus this thing, that's a negative number. So that's definitely not the one we want. We're looking for an index. We don't want something negative. So it's really the only solution we care about is the plus version. And that'll give us a positive number. How do we know that it's positive? Because this number here is at least 9, so its square root is at least 3. That takes care of the minus 3 there. So that's the solution we get. But what's the problem in general with this b? yeah, I mean, and this b is whatever this solves to, but in general, it's not an integer, right? I mean, why should it be an integer? That's okay. So b will give us something like, you know, if we put in I equals 4, then we will get something like b equals 2.432 something something. Is that useful to us? Yep. Yeah. If we just truncate this value of b, killing this part, that'll give us the index we want. So it'll tell you, yeah, it's basically, yeah. No, this will have integer solutions exactly when this thing crosses a boundary. Yep.
Wouldn't we need to take the seating note the door because we're looking for something breaches now?
So let's check. Well, no, let's not check. But if we take, for instance, I is equal to so if we take I equals 0, that's nice and easy. This is minus 3 plus 3 over 2 is 0. Gives us this thing. That's good. If we take I equals 1, that will give us minus 3 plus the square root of 9 plus 8. Don't know what that gives you. But it gives you what? Root 17. Yeah, root 17. Well, that's bigger than 1, right? Yeah. So this gives you a number bigger than 1. And so 1 point something, and indeed we want 1 in that case. Okay. So it's telling you that it's part way into this, the solution is part way into this array. Well, it should be right. So that if this was 16, this would be a 4 in here, right? So that would be minus 3 plus 4. Oh, half. You're right. So it's the ceiling. Good. We take the ceiling of this thing. So this gives you 1 point something, and then you take the ceiling. Not the floor. Good catch. Okay. So that's it. I mean, you solve this quadratic equation. It gives you an answer that makes no sense, but you round it up to the next integer, and you get the index b that you're looking for. Okay. So that we have the solution to over there. It's the ceiling of that expression, that thing over there. Okay. And now we're golden. So get I, basically the code is compute the value of b, compute the value of j, and now return. Did we give a name to this array? Let's call this one blocks. Blocks dot get the bth item dot get the jth item in that array. Okay. blocks.getB gives us the array, or actually, we don't even get it because it's just a straight array. It's just add j. Okay? So 2 calculations, one to figure out which block and one to figure out which position within the block. All right. So then how does set work? So if I want to set the ith value in the list equal to x, is it any more difficult than this? It's the same thing, right? I mean, the hard part is computing the values of b and j. And that's not hard once you've worked them out. You just go to the bth block and you set the jth value in that block to be equal to something. Yep.
Sorry, I have a question for computing J.
Yep.
At the end, you changed it back to +1.
Yeah. It's I minus the first index of the block. Okay. So that's as the same performance, at least asymptotically, as ArrayStack, but uses only square root of n wasted space. Okay. And now, if you are the kind of person who studies these things, you say, oh good, we got down from like n wasted space down to square root of n. Why stop there? Why not try to go to the 4th root of n or the 10th root of n or something like that? And well, it turns out that you can't. And there's a fairly easy argument, but it might feel strange to some of you because it's not a natural thing to prove what are called lower bounds on these kinds of problems. Usually as a programmer, you try and solve problems, not show that they can't be solved. But in this case, there's a fairly easy lower bound. And here's the theorem for you. Any data structure that supports any flavor of add operation. So anything that I can add elements to, forget remove even, and forget searches or anything else. Anything that I can add elements to must use some constant times square root n wasted space. Okay? So here's the proof of that. You take your data structure. So now I'm trying to reason about all possible data structures here. And I add n elements to it. So now in my data structure, there are n memory locations which store items that I've added. Okay? So there's 2 cases to consider. In the first case, so case 1, the data structure uses more than square root n arrays. So in this case, the data that you put into it is spread out a bunch amongst a whole bunch of arrays. More than square root n of them. So why is it wasting square root n space in that case? More than square root n arrays, and for each array I need, yep. For each array I need a pointer to keep track of it. If I don't have a pointer that points to it, it's lost and it's not actually part of the data structure. Okay? So uses more than square root n arrays means uses more than square root n pointers. So if that's case 1, what do you think case 2 is? Case 2 is it uses at most square root n arrays. Okay. So not very many arrays. So not too many pointers. So if I pack n elements into, let's say, k arrays, what can you tell me about the size of the biggest array? Imagine the arrays are pigeonholes and the elements are pigeons. Yeah. Yeah. So that means at least one array has size at least n over k. Now k is smaller than the square root of n, so that means that this is bigger than n over the square root of n, which means that this is bigger than square root n. So in this picture, one of these arrays here is of size bigger than or equal to the square root of n. Now, remember that I built this thing by adding elements one at a time. Sometime during this process of adding these elements, this array was allocated. And right at the moment when it was allocated, before I had a chance to fill it with anything, it was completely empty. So it was an empty array of size square root n, which means that it was square root n wasted space. Okay. So that's the argument. So when that was allocated, it was square root n wasted space. So it doesn't matter what you do, if you have any data structure that allows you to add things, and I don't care what other operations it supports, at some point when you add n items, you will be wasting square root n space, either on pointers or on one big empty array somewhere. There's no way around that, which means that we can stop now trying to save space on these array stacks. We're not going to do better than square root n. Okay, that's it for today.